All right, so welcome to Math 383 Complex Analysis. So this is lecture 23. And what we are doing today is we're going to be talking about the continuation of the zeta function. There's going to be many different ways of continuing it, depending on how much work you want to do and how good of a result do you want to get. We will primarily focus on the theta function and the continuation through the theta function. This is going to be a nice way to motivate our shift into Fourier series. I will talk a little bit about the Gregory-Leibniz formula, which we might have mentioned briefly before, but it is connected to the Riemann zeta function. And then when we're doing this, when you get something like the functional equation of the Riemann zeta function, you always want to know what is the source? Where does this come from? What is the miracle? And that's really what I want to emphasize today, the right ways of looking at things. So there are two cultural extra credit options. Anybody know what this is a photo of? Miracle on Ice. When was it? And who was playing? And what game was it? Good. If you had said finals, you would have lost. It was not for the gold, it was to get into the gold game. Excellent. All right.
What is that game?
It's Miracle on Ice. It was from the 1980 Olympics. It was at the height of the Cold War, and it was basically a bunch of US college kids took down the team of professional Soviet hockey players who had basically just won every game they had played and had beaten the Americans 10-3 earlier. But they say, well, they lost 10-3 2 weeks earlier, it wasn't that close. And so it was just absolutely amazing victory. A lot of the kids were from Minnesota and the Boston area, just college players. All right, anybody figure out who this is? Yes, Riemann. Okay, I don't know if it counts if I said it, but since I just confirmed it does count. Okay, so we are going to be talking about his zeta function. There are links to his papers, depending on what language you want to read them, you get to choose. I have just posted ones in German and English. I am sure you can find it in other languages. I know I've seen it in French before. You are getting to the point where it's worth looking at the original papers. And sometimes there are gems that have been passed on for a couple of centuries, where if you revisit them, you actually have an interesting chance. Manjul Bhargava, who was a classmate of mine at Princeton, now has a field, looked at some of the work of Gauss on class forms and was able to come up with some great stuff. So it is worth revisiting the masters every now and then and just seeing what they did. There's a little zoom in of the beautiful handwritten paper, which no one really wants to read. So it has been translated and teched up very nicely. Does anybody here speak German or read German? We'll find out. So when I was in graduate school, we had to be able to demonstrate mathematical proficiency in 2 out of the following 3, French, German, and Russian. And the reason was there was a lot of great papers written in these languages, and it takes an awful long time to change graduation requirements. And so if you go back 50 or 100 years, it's actually very good to be able to know those languages. How important is it nowadays? Much less. What can you do? Yeah, I mean, it is amazing what you can do. I mean, the iPads have reached the point where they mostly understand my Boston accent. I have to say prime numbers are not prime because it always translates prime as crime when I speak. But it does a good enough job. So if anybody wants to try to read the German, starting with Man findet. So I know we had one person who speaks German, but he told me he was not going to be here today. All right, so we'll go to the English translation. One now finds indeed approximately this number of real roots within these limits, and it is very probable that all roots are real. Certainly one would wish for a stricter proof here. I have meanwhile temporarily put aside the search for this after some fleeting futile attempts, as it appears unnecessary for the next objective of my investigation. What is that? That is the Riemann hypothesis. So I know that there are different statements and whatnot about professors that circulate, and I know sometimes there are comments about my going off on tangents and having asides. You want to talk about an aside? Yeah. This is the ultimate. Just casually mentioned, buried in a paragraph, not really explicitly formulating it. Yeah. This is the first introduction of the Riemann hypothesis. And what he was trying to do in the paper was just get the main term for how many primes are there up to x. And if all you care about is the main term, you only really care about, are there any zeros on the line real part of s equals 1? If you can show that there were no zeros there, that's enough to prove the main term. try to think. Let me be very careful on that. I believe that's all we need is that. I don't think we need anything a little bit larger than that. Okay. So here's a really good exercise to start with. So use the product expansion of the zeta function. So we can write zeta of s as the sum n goes from 1 to infinity of 1 over n to the s, or we can write it as a product p prime 1 minus 1 over p to the s inverse, to prove that the zeta function has no zeros for the real part of s greater than 1. I claim that this is really straightforward if s is a real number. Why is this straightforward if s is a real number? Yeah. Yeah, the sum is positive. I'm summing a bunch of positive terms, and the series converges, right? So it's not going to be that difficult. How do you know the series converges? Okay, p-test, integral test. That's using calculus. Can you prove the sum converges without calculus? So prove the sum converges for s greater than 1 without calculus. And there's actually a very straightforward proof that you can do here. And we're using the theme from last class, dyadic decompositions. Let's write the interval 1 infinity as a union, and goes from, I think, 1 to infinity of, maybe it's 0 to infinity, 2 to the n, 2 to the n plus 1. So we just break the integers up. Essentially, each block is twice the previous in terms of number of points. Why is this good? Well, if I look at the function 1 over n to the s, it doesn't really change that much from the left endpoint to the right endpoint. I can get upper and lower bounds very easily, because how much is it going to change by? So what's the maximum change on the interval 2 to the n to 2 to the n plus 1? 1 over. So if I look 1 over 2 to the n to the s versus 1 over 2 to the n plus 1 to the s, how much do they differ by? What kind of factor? Square, or the square root of it. Not the square root, because this is a general s. This is not. They differ by 1 over 2 to the s, right? Differ by 1 over 2 to the s. Really, they're essentially the same size. So if I want to look at the sum, n goes from 1 to infinity of 1 over n to the s, this is the same as the sum, n goes from 0 to infinity. The sum, say m, is in the interval in, 1 over m to the s. And then this would be less than equal to the sum, n goes from 0 to infinity. Let's just use the largest value in the whole interval. The largest value is if we take the left endpoint every single time. How many terms do we have in the interval? No, but how many terms are there in the interval? Well, the interval goes from 2 to the n to 2 to the n plus 1. So how many terms are in the interval? 2 to the n minus 1. I really don't want to write the minus 1. Let's just write this 2 to the n terms. And each term is at most 1 over 2 to the ns, right? Right? So this is just the same as the sum, and goes from 0 to infinity of, what is this? 1 over 2 to the s minus 1 to the nth power. What do we know about that? Geometric, and what can you tell me about the ratio? Less than 1, because s is greater than 1. So geometric series, as s is greater than 1, ratio is less than 1 converges. So we can actually show that this converges without resorting to calculus. It's good to get a sense of how deep is the result. We do not need calculus to show that this converges. And in fact, we can get a lower bound very easily as well, and we'll be within a factor like 1 over 2 to the s very, very easily. All right, so we know that the zeta function has no 0 when s is real. If you look at that sum and put an s complex, it's not at all clear immediately that this is going to be non-zero. As a nice exercise, use the Euler product to show that it is not going to be 0 for any s whose real part is greater than 1. So that tells us that there's no zeros of the Riemann zeta function with real part greater than 1. So we can now search for zeros to the real part of s is less than or equal to 1. The real part of s equals 1 is not too bad to do. There's some beautiful tricks. And then the rest is open. So the following is one of the most important theorems ever. It gives us the analytic continuation of the Riemann zeta function. It gives us a function that's defined basically everywhere with simple pole at s equals 1. And it basically says take the zeta function and multiply by this crap, and then you get the completed zeta function. And there's a couple of different ways you can do in terms of what you're defining the completed zeta function to be. Depending on which book, you might have a slightly different definition. It doesn't really matter if I put in the factor 1/2 or not. That just rescales everything. The s minus 1, sometimes people keep it, sometimes they don't. The advantage of putting in the s minus 1 is that gets rid of the pole. So now this function doesn't have a pole at s equals 1. The 1/2 s minus 1 is really not that important. It's the fact that you have gamma of s halves, pi to the minus s halves, zeta of s. That's what's important. And it turns out its value at s equals its value at 1 minus s. So if we know the zeta function when the real part of s is greater than 1/2, we know it when the real part of s is less than 1/2. This is very similar to the gamma function, where once we know it in a strip of width 1, we can use the functional equation of gamma. Gamma of s plus 1 is s gamma of s to get its value anyway. So this is what we want to prove. This is in some sense ideal because it now gives us the zeta function defined everywhere. So we can define zeta everywhere. We can use it everywhere. We don't have to worry as we're shifting contours and whatnot that we reach a spot where the function isn't defined. Okay. So before we prove the big result, let's, yes.
That's analytic continuation of zeta?
Of zeta.
So that is equal to zeta at all points.
No. It's not exactly equal to zeta because I put in some other stuff.
So it's not its analytic continuation, right?
It's the continuation of a function closely related to zeta. I modify zeta, and I have the completed zeta function. And the completed zeta function is very well behaved.
How does the completed zeta function work?
That's what's right here. That's the completed zeta function. Notice everything here is understood easily except for the zeta function. The 1/2 s minus 1 gamma of s halves pi to the negative s halves. We understand that very easily. It's a trivial modification. And so because we know how that behaves, if we know how the whole completed zeta function, we know how C behaves, from that, we can easily figure out what zeta is doing. It's just telling us that this is the easier object to study. When we did the quick sketch of the proof of the prime number theorem, we saw an analog of the eigenvalue trace lemma from linear algebra. And we saw when we did the logarithmic derivative and we did the geometric series expansion, we had a log p coming down. And we saw that it was easy to count not how many primes are less than or equal to x, but how many weighted primes are less than or equal to x, where the weight is equal to log p. And so a lot of times when you're trying to investigate, you're trying to figure out just what is the best thing to study. I'm not quite sure how we actually have 2 hours on the screen. This is quite interesting. It must be extremely important. Okay. So here is a simple continuation. So this is an easy continuation of zeta of s. So remember, initially the zeta function is only defined when the real part of s is greater than 1. Let's look at the following. So the proof proceeds by divine inspiration. So let's look at zeta of s and let's subtract 1 over s minus 1. Why might this be a good thing to subtract? Yes.
Hold on one.
Yeah, it has a pole at 1. And we believe it has simple pole of residue 1 at 1. So if we subtract that off, hopefully this will be nice. And hopefully we'll have a nice, holomorphic function when we subtract this. And then if we have a nice holomorphic function, then maybe this will be defined on a larger region than just the real part of s is greater than 1. The function 1 over s minus 1, that definitely has a pole at s equals 1. But away from that pole, is this function well behaved? Yeah. Do we understand this function quite well, right? All right. So the next step, it's equal to the sum of n to the minus s minus this integral. Well, zeta of s is just defined as a sum, so that's no problem. The first part is just the definition of zeta. Now, when I have n goes from 1 to infinity, and I have these integrals from n to n plus 1, they all add together, and that's the integral from 1 to infinity. What is the integral from 1 to infinity of x to the minus s dx? Yeah, this becomes x to the negative s plus 1 over negative s plus 1 evaluated at 1 and infinity. And since the real part of s is greater than 1, when we put it in at infinity, we get 0. Yes, good. And so we just get negative 1 over 1 minus s. But that's just the same as 1 over s minus 1. And because the real part of s is greater than 1, we have no convergence issues. So we can just do this in intervals of length 1. This is a little bit similar to the dyadic decomposition. The dyadic decomposition, I had my intervals doubling in length every single time. Here, I just have intervals of the same length. Each one is of length 1. And I look at what's going on in each interval of length 1. And so for each one of them, the integral of x to the negative s is giving me a little bit of a contribution to the 1 over s minus 1. And then, well, n to the minus s, I can regard this as a function of x, right? What kind of function is n to the minus s as a function of x? I'm sorry? It is a polynomial, but n to the minus s is a very special kind of polynomial. Constant, right? It's a constant function. So if I integrate from n to n plus 1 of the constant function, it's just that value times the length of the interval. So what I'm really using is I'm using n to the minus s is n to the minus s times the integral from n to n plus 1 of just 1 dx. And that allows me to put both of them under the integral sign. And so now I just want to ask, how close is n to the minus s to x to the minus s? Well, when x equals n, the difference is 0, right? The worst case is going to be when x is all the way up to n plus 1. So now this is just doing some simple analysis to just see how far apart can they be. And so, one of the standard calculations is you just get s times the integral of y to the negative 1 minus s. There's lots of different ways you could do this. But when the dust settles, you get that this difference is bounded by the absolute value of s times n to the negative 1 minus sigma. Yes?
If you divide both sides by n to the negative s, you get 1 equals that integral. Is that true?
Should be. I mean, because when you integrate,
Why is the integral equal to 1?
the integral is not equal to 1. Just when you integrate it, when you integrate, you're going to get y to the negative 1 minus s plus 1. So that's going to be y to the minus s. And then you evaluated the two endpoints, and you should get n to the minus s minus x to the minus s. So you should be able to get this just by doing the integration. Yep. The integral here should just be y to the -1 minus s plus 1 over -1 minus s plus 1 evaluated at n and x. And so when you plug that in, this is actually giving us something that's exact. You could, of course, do other things to try to estimate. It's nice that we actually have something that's exact. And so now we have its, at most, the absolute value of s, which is no problem, times n to the -1 minus sigma. And so now if we feed this in, we would have it's less than equal to the sum, n goes from 1 to infinity, absolute value of s, and then it would be 1 over n to the 1 plus sigma. When does this converge? For what values of sigma does this converge? Yeah, so converges if sigma is greater than 0, we have continued zeta of s to the real part of sigma is greater than 0 from the real part of sigma greater than 1. So initially, our formula for zeta only worked when the real part of s was greater than 1. This formula actually works so long as the real part of sigma is greater than 0. It is not the best continuation possible, but we got it with very little work. This is a general theme in mathematics. There's often low-hanging fruit. If you don't use too much, you can get some results very quickly. But if you want the most powerful results, not surprisingly, you have to throw the whole kitchen sink out. All right. There's lots of other kinds of continuations you can do. This is the eta function. And here is another way to continue the zeta function. And so what we're going to do here is we're looking at the alternating zeta function. Now, one of the reasons the Riemann zeta function gives us trouble is as s goes to 1, what series do we get for the zeta function? Harmonic, and the harmonic blows up. But what is true about the alternating harmonic series? Convergence. So the idea is maybe we can use the alternating harmonic series to gain convergence. There's a beautiful paper on random harmonic series, where what you do is instead of having 1 over n or -1 to the n over n, you have epsilon n divided by epsilon sub n over n. So epsilon is a coin toss, independent of the others, with a plus or minus sign. And you can say with probability 1, a random harmonic series converges, and you can talk about what do you expect it to converge to. And I know some people who've done small with me have read that paper, beautifully written paper in terms of the results that you get. So let's look at zeta of s. It's 1 plus 1 over 2 to the s, plus 1 over 3 to the s, plus dot, 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 at least as long as the real part of s is greater than 1. And let's look at eta of s is going to be 1. So again, let's be very careful. When you start off with n equals 1, you have -1 squared. So you start off with 1. So you have -1 over 2 to the s, plus 1 over 3 to the s, minus dot, dot, dot. Okay. So when you see these, depending on how we choose to combine things, we can have a lot of simplifications. Right? If we were to just add them right now, what would happen? So if we just add them, what would you get? So you get 2 times the sum of the odds. So if you add, you get 2 times the sum of the odds. What if we subtract it? Then you would get 2 times the sum of the evens. Which would you rather have, sum of the odds or sum of the evens? Why evens? Yeah, because you can factor out 2. And so what we're told is to try looking at 1 minus 2 to the 1 minus s zeta of s. So what would be 2 to the 1 minus s times zeta of s? This would be 2 times 1 over 2 to the s times zeta of s. right? So this is going to be 2, 1 over 2 to the s plus 1 over 4 to the s plus 1 over 6 to the s, right? Because before I had 1 plus 1 over 2 to the s plus 1 over 3 to the s, everything gets multiplied by 2. So if I look at zeta of s minus 2 to the 1 minus s zeta of s, I would have zeta of s is just 1 plus 1 over 2 to the s plus 1 over 3 to the s plus 1 over 4 to the s plus dot, dot, dot. And then we would subtract off 2 to the 1 minus s zeta of s. So the first one would be 2 times 1 over 2 to the s. And then the next one would be 2 over 4 to the s, and so on and so on. And so when you subtract, you would just get 1. Then you would get 1 over 2 to the s minus 2 over 1 over 2 to the s. So you would just get minus 1 over 2 to the s. Then you would get 1 over 3 to the s. Then you would have 1 over 4 to the s minus twice that. So you get 1 over 1 minus 4 to the s, and so on. And that's just eta of s. And so this is the proof that the zeta function times 1 minus 1 over 2 to the s equals the eta function. So we get zeta of s is 1 minus 2 to the 1 minus s inverse eta of s. If you look at 1 minus 2 to the 1 minus s, okay, I'm taking the inverse of that, so I have to be careful that that's not 0. What would I need for 1 minus 2 to the 1 minus s for that to be 0? What would have to be true about s? Equals to 1. Yay! Right? The zeta function is supposed to have a pole that s equals 1. The eta function is well behaved. Good. This has a pole that s equals 1. Good. Blows up at s equals 1. Excellent. And eta of s, with a little bit of work, you can show that this is well defined. Eta of s converges if the real part of s is greater than 0. So I'll leave that as an exercise. It comes down to the fact that we have an alternating sum. And so because we have an alternating sum, if you do partial summation, everything's going to work out beautifully. And this is another way to continue the Riemann zeta function. There are a lot of, I should be careful because this is being recorded. There are a lot of ambitious attempts to prove the Riemann hypothesis. Many of those attempts involve playing games with series expansions and using those series expansions where they may not be legitimate. Okay, so what is 1 plus 2 plus 4 plus 8 plus 16? Somebody tell me so I can stop writing all of this. Now I'm going off to infinity. What is this equal? Nope. -1, right? Because the sum of x to the n, and goes from 0 to infinity, is 1 over 1 minus x, take x equals 2. So the sum is so large, it goes past positive infinity, comes up through negative infinity, and almost makes it back to 0 before it just peters out. Is anybody convinced that this equals -1? So this is the nature of, continuation. We start off with a series, the sum of 1 over n, the sum of x to the n, and it equals the function 1 over x. So in the region where they're both defined, I can use either one. However, the function 1 over 1 minus x makes sense for all values of x other than 1. And so in some sense, we can talk about, well, what does it mean to sum the powers of 2? Who here has done any algebraic number theory? What word can I say to actually make this legal? periodically. So has anybody done the periodics? So if you've done the periodics, if you look at this with the prime 2, it is legal. Because when you do things periodically, the higher power of the prime you have, the smaller it is. And so there is actually a way to make this reasonable and interpret. Okay. So we've already done, do you believe in miracles? Who can give me the movie that has the line, do you believe in unlikelihoods? People had seen the movie in probability, but no one was able to give the name for him. They're playing it on ESPN 8 the Ocho later tonight. Anyone has seen Dodgeball? Dodgeball. I don't want to give away the movie because it's such a suspenseful movie. Beautiful line. Where is the miracle coming from in the Riemann zeta function's continuation? Where we can now have this function defined for the entire complex plane at modulo of pole, say at s equals 1. So it comes from the theta function. And the theta function is defined as the sum from -∞ to infinity of e to the negative pi n squared x. And again, from this point onward in the semester, as we look at Fourier analysis, there will be 3 different ways of defining Fourier transforms. There will be lots of different freedoms depending on where do you want to put your pi's or not. And so it's just something you're going to have to just pay attention to. Now, if you look at this, you notice that the theta function is pretty symmetric. As I go from -∞ to infinity, well, every value is taken twice, once positive, once negative, except for 0, which only happens once. So I could write it as 1 plus twice the sum from 1 to infinity. And so we're going to let omega of x be theta of x minus 1 over 2. And effectively, this is just going to be the sum n goes from 1 to infinity of e to the negative pi n squared x. Now, we talked about how the gamma function satisfies a functional equation. It turns out the theta function satisfies a functional equation. Theta of x inverse, theta of 1 over x, is equal to the square root of x times theta of x. And not surprisingly, if theta satisfies a functional equation, omega should satisfy a functional equation. And you should be able to get this by just substituting in and just doing some algebra. So when you do the algebra, you get omega of 1 over x is minus 1/2 minus 1/2 x to the 1/2 plus x to the 1/2 omega x. So the real heart of the argument is, why does the theta function satisfy this strange relation? Theta of 1 over x is related in a very nice way to theta of x. 1 over x and x are multiplicative inverses. So what we're really saying is, we know a function at x, we know its value at its multiplicative inverse, and there's a simple rescale of the square root of x. All right, the first thing is, whenever I write a function down, what should we do first? What must we make sure? I'm sorry? Yeah, it's well defined. So is theta of x or omega of x well defined? So let's study omega of x, which is the sum, and goes from 1 to infinity of e to the negative pi n squared x. Clearly, this is non-negative. So the question is, does this sum converge? Can anybody see something that we can use to dominate this? So you could try a Gaussian. Now, a Gaussian is continuous, this is discrete. You could try to play games with that, but then that would require you to know that the Gaussian converges, or it would require you to use the area under the Gaussian. So that is a possibility, but it would still reduce to then you need to know that this is converging so rapidly that it integrates to something finite. So that's one route, but there is a nice elementary series that we can use to dominate this. So this is going back to parts of multivariable calculus, where you try to show that a series converges. What are the different tests we have for series convergence? Ratio test. What else? Integral test. Comparison. Root. So the root and the ratio test are basically like the quadratic formula. There is really no creativity involved. You just plug it in and you do the algebra. The comparison test, that's the art. That's when you're trying to look at a polynomial and just see how it factors. Oh, it's x minus 1 times x minus 4. Really, the root test and the ratio test are actually just comparisons with a geometric series. That's what's lurking in the background, is that there's a geometric series that's being compared. It just figures out which geometric series to compare it to by calculating either the ratio or the root. So can you think of a good series to compare this to term by term that will be larger than this? Yes. Okay. I'm going to just write it initially either the negative pi n x, which is what you've said. And what we're doing is I'm just replacing the n squared with just n. That's going to make it smaller. I said that's going to make it larger because I now am raising it to something that's not quite as large. And this is the sum, and goes from 1 to infinity, of 1 over e to the pi to the n. So it's a ratio test. Ratio is 1 over e to the pi, which is less than 1. So it does converge. So for any fixed value of x, it's fine. What is the only value of x I have to be careful about? Yeah, so if x equals 0, trouble. As long as x is not 0, we're fine. What would happen if I... Oh, we would never do that. All right. Why wouldn't we take x to be negative? Well, we have e to the negative pi n squared x. If we took x to be negative, it's clearly not going to converge. Each term is getting larger and larger and larger. It's going to explode. So as long as x is greater than 0, everything is fine. So a lot of times, this sadly happens, but there's one point you have to be careful about. And so what you might have to do technically is you might have to integrate not from 0 to infinity, but you might start off at epsilon and go from epsilon to infinity, and then you take the limit as epsilon goes all the way down to 0. Okay. So let's talk a little bit about how we would prove the functional equation. So we start off with the gamma function. Gamma of s is the integral of e to the negative t to the s minus 1 dt. And the claim is that the integral from 0 to infinity of x to the 1/2 s minus 1 e to the negative n squared pi x dx is gamma of s halves over n to the s pi to the s halves. If that's true, so let's just assume that this equality on the right holds. What would you want to do to both sides if this is true? I'm sorry? So if we have this equality, what should we do to both sides? We're trying to get the Riemann zeta function. Not multiply by the zeta function. It's not multiplying. Sum of all positive n. Look at what we have on the right-hand side. We have gamma of s halves, which is nice. We have pi to the s halves and then, oh, that's our pi to the negative s halves. And then we have a 1 over n to the s. This is essentially looking like the zeta function just at one integer. It's looking like a part of the zeta function. So we would want to sum this over all n. And if we sum this over all n, then we're going to get, so sum over n, the right-hand side is going to be pi, I'm sorry, gamma to the s halves, pi to the negative s halves, zeta of s. And then the left-hand side is the integral from 0 to infinity, x to the 1/2 s minus 1. And then we'll have a sum, and it goes from 1 to infinity. Oh, that's what we're calling omega of x. Oops. So then that would be omega of x dx. So if this equality is true, we now have a way of relating the zeta function to an integral. And if you look at this integral, omega of x has really nice decay as x becomes very large. We have to worry a little bit about what happens as x goes to 0. Okay. But the idea is we're going to try to replace the zeta function with an integral that's easy to work with. So we just have to prove this identity. So how do we prove the identity? Well, we have dm of s halves n to the s pi to the s halves. Let's just put in what dm of s halves is. It's just n to the negative s pi to the negative s halves, and then the integral from 0 to infinity e to the negative t to the s halves minus 1 dt. And this is going to be equal to n to the minus s pi to the minus s halves dm of s halves. Okay. Does this look like, are there any questions? All I did is I just wrote out what dm of s halves is. I just took, the claimed identity, the gamma of s halves over n to the s pi to the s halves, and I just said, well, let's just replace gamma with the integral definition. And now we use the fact that we have a huge hint screaming at us, right? We're trying to show that this equals the integral of x to the 1/2 s minus 1 e to the negative n squared pi x. Which term do you think is going to be the easiest to match? I'm going to change variables. Maybe send e to the minus t to e to the negative n squared pi x, right? Is this a reasonable, if I want to get these two to match, let's get the exponential factors to be the same. So what change of variable do I want? I want t to equal n squared pi x. So dt is going to be n squared pi dx. As t goes from 0 to infinity, what does x go from? X is also going to go from 0 to infinity. And so we get n to the minus s pi to the negative s halves, integral x goes from 0 to infinity. E to the minus t becomes now e to the negative n squared pi x. Now we have t to the s halves minus 1. So that's going to become n squared pi x to the s halves minus 1. And then dt becomes n squared pi dx. Boy, this is looking a lot like what we want. So we have n to the minus s, pi to the minus s halves. Now we have an n squared to the s halves minus 1. That becomes a n to the s minus 1, right? N to the s minus 2, sorry, n to the s minus 2, right? But then we have an n squared, so we pull out an n to the s. We have a pi to the s halves minus 1 times a pi, so that gives us a pi to the s halves. And then we just have the integral x goes from 0 to infinity, e to the negative n squared pi x, x to the s halves minus 1 dx. And that's what we wanted to prove, because all of this stuff over here equals 1. So there's a lot of different ways of doing this calculation. This was the method of divine inspiration, where we knew what we wanted to get at the end, and so that influenced what I wrote down. It's really coming from the definition of the gamma function. The gamma function has a nice integral representation. And so we can pass from a discrete sum to an integral. Why are integrals better than sums? Calculus, we have all these tools from calculus and analysis to deal with these continuous processes. And so now that we have that, the rest of the argument is not too bad. We now have, if we sum over all n, we have the following expansion. And now, wait a minute. So, okay, when we sum this, we're going to be summing over n positive, and that's going to be our omega of x. And I think over here, this should be actually, I think it should be a 0, not a 1 for the integration. Okay. And now what we do is we use the fact that we have a nice formula for omega of x. We can relate omega of x to omega of 1 over x. So you always want to see, what is the source of the miracle? Well, I'm integrating from 0 to infinity. How can I get this to use an x to a 1 over x? Well, what I do is I write the integral from 0 to infinity as the integral from 0 to 1 plus the integral from 1 to infinity. And now, when I have the integral from 0 to 1, the integral from 0 to 1 of, let's say, f of x dx, change x to t equals 1 over x. And then as x goes from 0 to 1, where does t go from? So if x goes from 0 to 1, what will t go from? Infinity to 1. So modulo signs that are going to come in, this integral is then going to eventually look like something like the integral from 1 to infinity of f of 1 over x. I guess we're calling that now t. 1 over t, sorry, 1 over t, blah, the Jacobian coming in here, dt. And what happens when you just go through the algebra is we now have this integral written as an integral from 1 to infinity. And now instead of having our function at x, we have a function at 1 over. Oh, wait a minute. We've got something on the right-hand side that relates the values of omega at 1 over x to the values of omega at x. And so the other integral from 1 to infinity had our function against omega of x. And now this has our function against omega of 1 over x, which we can convert to omega of x. And so again, I'm not going to go through all the algebra, but when you finish and you do all of the simplifications, at the end of the day, when the dust settles and you use the functional equation of the omega function, you're going to get a 1 over s minus 1, and then you're going to get this nice integral. When you look at this integral, we now have x goes from 1 to infinity. Omega of x is the sum and goes from 1 to infinity of e to the negative pi n squared x. For what values of s will this converge? So for an integral, I have two potential pitfalls that can stop it from converging. One is that it might not decay fast enough as I go to infinity. And the second is there might be a point where it blows up. Does x go all the way down to 0? No, x goes from 1 onward. So there's no danger of things blowing up. The x to the 1/2 s minus 1, x to the negative 1/2 s minus a half, those aren't going to blow up. So no blow-ups as x is greater than or equal to 1 and decays rapidly as x goes to infinity. This converges for all s. The integral, yes. The integral converges because we're not going from 0. And that's the brilliance of this method, is that when things are near 0, things are problematic. So we go from 1 to infinity. And so we use this multiplicative structure. We write 0 to infinity as 0 to 1 and 1 to infinity. And if you flip things, 0 to 1 is really the same as 1 to infinity when you change variables. Yes. Nope. I'm only talking about the integral. Yeah, but I'm talking about the integral. Yeah, but I'm talking about the integral. Okay, so we're talking about different things. The integral is fine. The 1 over ss minus 1 has a pole at s equals 0 and it has a pole at s equals 1. I agree completely. This, it's the integral, so I will write the integral converges. Well, the integral is defined for all values of s. And the 1 over ss minus 1 makes sense for every value of s other than 0 or 1. And so what this tells us is this completed function, the pi to the minus s halves gamma s halves zeta of s, is equal to a nice piece that converges for all s and a piece that has a pole at s equals 0 and s equals 1. Now, if you try to think about what's going on with the gamma function, it turns out, well, we don't have time to talk about the values of the gamma function, so I will just leave it at that. And so this gives us a continuation of the zeta function to the entire complex plane with poles at s equals 1 and maybe s equals 0. Because there could be problems there, but other than that, everything is fine.